Okay, so I am going to describe some properties of the Jacobi theta function. So so this is about the Jacobi theta function. Or I'm actually going to do a variant of the Jacobi theta function, which is the variant that we're going to be using. But let me just write down the Jacobi theta function first. So, so the Jacobi theta function it's the following series. Okay, so it's minus I q to the 1/8 sum n over the integers -1 to the n q to the n times n plus 1 all this over 2 w to the 2n plus 1. Okay, so this is the Jacobi theta function. You can view it as a complex analytic function, or you can view it as a p-adic analytic function where this q here, this p-adic norm is less than 1. Okay, before I get too boring, let me just say what I'm doing here is I'm moving towards a geometric description of the theta function from Machizuki's Etale Theta paper. Okay, so I want to describe the zeros and the poles of this thing. What it amounts to is kind of taking a version of the Jacobi theta function that I'm doing right now, normalized, and make it so it's kind of integral, so that I can reduce it mod p. Okay, then there's a space on which it lives, and it'll turn out that there's kind of this thing is kind of characterized by its zeros and its poles. It's not kind of, it is, and the zeros are these horizontal things corresponding to these marked points. Okay, maybe there's another one there. Okay, and then the zero or the poles will just be completely on the special fiber. Okay, and they'll have a Gaussian order. Okay, so depending on which component you take. Okay, and so these are the poles. Okay, and then the zeros are these cusp things corresponding to these marked points on this curve. Okay, so that's what I'm going towards. I'm going towards the geometric description of the divisor of the theta function appearing in the Etale Theta paper. All right, that's all I want to say about that. Okay, so I wasn't quite done. I needed to add something else. So I needed to add what the purpose of doing this is. So the end game is that we're going to have this theta function, and there's this Kummer classes associated to meromorphic functions, and this allows you to essentially associate a cohomology class to these guys. And the property, the interesting property is that one of the interesting properties of this is that one is able to evaluate the cohomology class and get out numbers. And it turns out that when we evaluate these theta functions, we're going to get out Q parameters, essentially, or roots of Q parameters. And this is interesting for us because this is one part of the Spiro inequality. All right. So the whole process will be about reconstructing these parameters, and what these zeros and poles things will do, it'll allow us to construct these these fractions, which will then be interpreted as morphisms of Fabrenioids. Tempered Fabrenioids. Morphisms not of Fabrenioids, but in Fabrenioids. So we'll have objects in these categories, and morphisms between these objects will encode these zeros and the poles, which will then let us reconstruct this theta. So that's the basic idea. Okay, so now moving forward, I'm going to go and continue and now prove some elementary properties about this Jacobi theta function. Okay. So, to get things going, I want to describe some properties of this. I'm first going to give a lemma. And so the lemma, this is the triple product formula. And So this can be found in like Whittaker-Watson. So Whittaker-Watson is this book on special functions. That's kind of old school, but it's really cool. So I'm going to write down this triple product. Surprisingly, in the triple product formula, you need to write down a triple product. 1 minus q to the n over z. Okay, so here's the triple product. The triple product formula says that there's this identity here. And so this is, okay, so you can prove this, however you want, but this is an identity of formal power series. So it's like completely general. It doesn't matter what these things are. They're just symbols as far as I'm concerned. Okay, and it's true that this holds. Okay. So now using this, we can derive a product formula for the Jacobi theta function. Okay. All right. So how do we derive the product formula for the Jacobi theta function? Well, I'm just going to kind of write out something, and I'm going to tell you that then we're going to find that it's Jacobi theta function. So I'm just going to write something out. This looks familiar, right? This maybe not so much. Okay, n greater than or equal to 1 minus q to the n. 1 minus q to the n w squared. N greater than or equal to 1 minus q to the n over w squared, like so. Okay, so this is equal to I q to the 1/8, 1 over w. Okay, I am just applying here the triple product formula. Okay, so that's the triple product formula. This is starting to look like it. So it turns out that, so what do? We do I q to the 1/8, 1 over w, and now we shift the index. Okay, so negative 1 to the n plus 1, and then we do q to the n plus 1 here. This just becomes n divided by 2, w to the 2n plus 2. Okay, and now this becomes I to the q 1/8. Now that there's two of these, we can get rid of one of them. Okay, so we'll just get rid of one of them, and here we just have the same thing. So this is n. Okay, so now it's pretty clear that we have 1 to the n. Okay, so now let's pull the minus out. Q to the n plus 1 times n divided by 2, w to the 2n plus 1. Okay, so now this is this is exactly what we had before. This is the Jacobi theta function. Here, so this is theta 1. That's the Jacobi theta function. Great. So we can just now using this, we can just kind of read off some properties. Okay, so I don't know what we. Okay, so the Jacobi theta function is related to there's a certain other theta function that Machizuki uses that's normalized that I'm more interested in. And it's the following theta function. Q to the minus 1/8, sum n integers, q to the 1/2, n plus 1/2 squared. And then we have w to the 2n plus 1. Okay, so there's this series, and then we have our other series. The other series was, let me just write it down again. So it was minus I q to the 1/8 sum for n in the integers, q to the, what do we have? N times n plus 1 over 2, w to the 2n plus 1. Okay, so it turns out that just by expanding this out, so if you do n plus 1/2 squared, just this becomes 1/2 n times n plus 1 plus 1/8. Okay, so so this part here. Okay, so what happens when you well, let me just write out the formula. It turns out that using this, that you just have that theta 1 of w is equal to negative I q to the 1 over 8 theta dot dot w. Okay, so there's this kind of fundamental relation between these two things. All right, that's nice. So what? Okay, so this is going to give us a nice formula for the Machizuki's Jacobi theta function, or the normalized Jacobi theta function, and this one's also going to be integral. So we go back and we look at our infinite product here. Okay, and I'm just going to use this infinite product, and I'm going to derive an infinite product for the one that's going to be used in the Etale Theta paper. Okay, so this is minus 1 over w product of n greater than or equal to 1, 1 minus q to the n, product n greater than or equal to 0, 1 minus q to the n w squared, and then we'll have one more factor, n greater than or equal to 1, 1 minus q to the n divided by w squared. Okay, so this is this infinite product formula for Machizuki's Etale Theta, or the normalized Jacobi theta function. So this shows a couple things. So we can read off properties. Easily. So from this thing. So the zeros of this guy are exactly the set of q to the j over 2, where j is an integer. So these all occur with multiplicity 1. That's easy to see. And the other thing that we see is that we can't really make this simpler. So we can't make this simpler by... Let me say what I mean. This simpler. So I have to do the square root. The square roots here for the q's. If we considered square root of w instead of w, we get something that's non-algebraic. Okay, so geometrically what this means is that we're going to have to go to some cover of the natural domain of this. And this is actually going to be something that's defined on it's going to be a meromorphic function in the multiplicative group. Okay, so there's also some nice functional equations here. So let's compute a functional equation. So let's do this. What happens when we do this? So here, if I do q to the 1/2 w, right? So I'm just going to plug in everything like the formula that we know. So we have this. This is this constant term, and then we have 1 minus q to the n, and then we have q times w squared. Okay, and times, and then we have the last term. So we have the zeros here, 1 minus q. Okay, now we do n minus 1 over w. Okay, so I'm just going to call this whole constant here c. Okay, so that's just a constant. But what do we find? We find that after we do this, so here this is actually, we're missing a term. And then here we're getting an extra term, so we need to make up for this. So and then we have this q to the 1/2 here. So let me write what that is, what's going on now. So, okay, so we have this term here. This guy is just the same old constant. This guy is now missing a term. Okay, so in order to put the term back in, we need to divide by the term. Okay, the term that's missing is 1 minus w squared. Okay, this one here has an extra term, so we can just peel it off here. So the extra term is, so that's a squared. What's the extra term? 1 over 1 minus w squared. Okay, and then we have our usual theta function here. Okay, the Jacobi theta function, the normalized Jacobi theta function. And, okay, so actually if I put that there, then I have to get rid of this, because this is the extra factor. So we have the two parts here, plus that constant, plus the 1 over w. So that would be a positive now. Okay, so now this becomes 1 over q to the 1/2, and this is, so w squared minus 1 over w squared, and then we have this 1 over 1 minus w squared, so theta dot dot w. Okay, and now we can see what we get. So putting this all together, these two things cancel to give you a minus 1. And we have that theta of q to the 1/2 w. So this is just equal to negative 1 over q to the 1/2 w squared theta dot dot of w. Okay, so this is a relation that we have for the this normalized Jacobi theta function. There's some other properties that we can derive. Okay, so for example, in this formula here, what happens if we put w is equal to the square root of minus 1? So this is kind of an important property in our applications, because these will correspond to this situation will correspond to a torsion point. So let's do that. So dot dot, and then we have so square root of minus 1 q to the 1/2 here. So we just get this part here. So we just get 1 over q to the 1/2. Then this is minus 1 squared, so this is a minus 1. And then we have theta dot dot over square root of minus 1 here. And so this is just 1 over q to the 1/2. Okay, and this tells us that theta dot dot of the square root of minus 1 q to the 1/2, this is going to be equal to, or divided by, this thing here. So this is 1 over q to the minus 1, like this. Okay, so we have this formula here. Sometimes this function here, Machizuki calls this theta double underlined of w. So this is theta dot dot of w normalized again, like this. Okay. Okay, so there's this thing, so where we evaluate it at a torsion point, we can recover this value of the q parameter. Okay, that's kind of interesting. I mean, not so interesting, I mean, just completely elementary. There's other things that we can do. So, for example, one can check that the following identity. Okay, doing the exact same thing that I did. So you use just kind of the basic expression. So maybe it's a good exercise to do that. This is equal to minus. Okay, so you use the exact same expression. So you plug it into, so you take, again, the series formula here, or this product formula, and then you plug in 1 over w everywhere. Okay, and then when you get the 1 over w everywhere, you'll find some magic cancellation, and you'll end up getting this. Now I want to talk about the zeros and divisors of this normalized Jacobi theta function here. So again, this is q to the minus 1 over 8. This was the sum over the integers of q to the 1/2 n plus 1/2 squared u dot dot to the 2n plus 1 times negative 1 to the n. Okay, so this is this normalized Jacobi theta function. And so I haven't really been telling you where it lives, but it's actually a meromorphic function on this space that I'm going to call y dot dot. Okay, and so so let me kind of back things up a little bit. Okay, so we have these elliptic curves, and we have this Tate uniformization. So x is an elliptic curve. So this is an elliptic curve, or an elliptic curve with a marked point at the origin. And there's a rigid analytic map. So this is all going to be, let's say, over a local field. Okay, so this is going to be isomorphic to, so it could be k cross q to the z, like so. Okay, so and we have that absolute value of q, this p-adic absolute value is less than 1. Okay, so this is going to be a non-Archimedean local field of mixed characteristic p. And, okay, so we have this thing, and this is really k times, like so. And there's this map here, which is well, some sort of composition of the Tate uniformization. And, okay, so we wanted to make this theta function here, but as we saw that we had this kind of crazy product formula, and the crazy product formula, so we had this function, okay, so this thing was given by this product, so there is some constant here. Then we had the product of n greater than or equal to 0 of 1 minus q to the n w, or u dot dot squared. Then we times the product of n greater than or equal to 1, 1 minus q to the n u dot dot squared, like so. Okay, and then just for completeness, this c was this product for n bigger than or equal to 1 of 1 minus q to the n, like so. Okay, so we had these guys here, and again, we couldn't, so this guy normally has parameter u, and then it goes down here, but we're going to have to take some sort of square root of this to get a new cover, y dot dot rigid. Okay, this is also going to be another copy of the multiplicative group, and here is where our function lives, our Jacobi theta series. It lives here kind of out nicely because we don't have to take any branches. Okay, so we talked about what we can read off from this, but I want to talk about how we can read off even more about these zeros and divisors. And what I'm going to do is I'm going to kind of thicken this situation on the left to some formal models. Okay, so again, we can take x. So maybe I'll start here. Okay, we'll start here. X is going to be a formal model or a semi-stable model of our elliptic curve x with semi-stable reduction. Okay, so for rigid so for formal schemes, right? The way that you can view them is they're kind of like some thickening. There's some kind of a tubular neighborhood of the special fiber of some model. Okay, so here's our formal model. or so here's the nodal reduction, then here's in the generic fiber, it looks okay. And then the formal scheme is kind of some thickening of this. Okay, and then we have, above this, we had this, so this is kind of X rigid, so this is the rigid analytic generic fiber of this. So this is X ridge. Okay, and above this, we're going to have some copy of GM. I gotta write it like this, I don't know. So this is Y ridge. Okay, and it turns out that we can actually thicken this up, or we can thicken this whole thing up to give some formal model here. So this is the special fiber, and this is the generic fiber. The generic fiber here is just a copy of GM. I kind of want to, eventually we're going to go to the double dots, but I kind of want to describe the undotted situation first. Okay, so this is a P-formal scheme. This thing is over maybe SPF of OK. Okay, so this is a complete discrete valuation ring. Okay, so there's a couple ways to describe this model here. So I'm going to denote by little k the residue field. So here's the special fiber here. And then you have a bunch of different components. And then here's, let me just kind of draw this. This is the generic fiber. So this is maybe the rigid generic fiber. This actually exists as a scheme. So you could draw it if you wanted to as a scheme. So you can think of it, there actually is a genuine scheme structure here. And so here at each of these parts here, so there's a bunch of different irreducible components here. This goes on infinitely. So I'm going to denote this yk0, and then here we're going to have yk1, yk2, etc. And then we can have, say, this guy down here is yk minus 1, and this could be yk minus 2. Okay, so there's all these different irreducible components, and they're all isomorphic to P1 over the residue field. Okay. Okay, and what's kind of interesting here is that, like before, we have we're going to have this action that gives us this quotient. Okay, so we can have q to the 0, q to the 1, q to the 2, q to the minus 1, q to the minus 2, and so on and so forth. And this is also going to have a discrete action. So this keeps going, this keeps going. Okay, this part here also has a discrete action, and what happens is that these guys get all shifted about. Okay, and okay, so that this kind of specialization is equivariant with respect to this discrete action. But let me kind of describe. So here, I guess, is the y0 component. Let me describe kind of what's happening here. So what's actually going to happen is that you're going to have these specializations here, where, okay, this guy specializes here, and this guy specializes here. Okay, and okay, so these are all going to be horizontal, but this is going to be special. So there's kind of this U parameter here, but each one of these families, each one of these copies of P1 have their own parameter. So the normal coordinate, we'll think of like the finite coordinate as being the U coordinate, and then the infinite coordinate as being the V coordinate. So V is equal to 1 over U0 on their intersection. So that would be if we remove these two pieces. Okay. But we can also kind of describe what's going on in the situation of one of these neighborhoods here. So in these neighborhoods, well, we're going to be gluing the point at infinity of this P1 with the point 0 at this P1. And this amounts to the equation, let's say V0. So this is the chart at infinity for this guy. So again, V0 is 1 over U1, 1 over U0. And so, okay, so when this is infinity, this is 0. Okay, so this is going to be times U1 is equal to, well, it's going to be Q, okay? so at each one of these things, it's going to be glued to Q. So for example, in the next neighborhood down, here we're going to have the equation V1 U2 is equal to Q, and so on and so forth. So that's how all of these things are glued. Okay, so let's look at what this means. So okay, so let's kind of write down what this means. So V0 is 1 over U0, and okay, so then V0 U1, so this is, well, we said that this was Q. Okay, so this tells us that U1 is equal to Q U0. Okay, so how did I do that? So I just kind of divided over on this side here, and then 1 over V0 is Q0. Okay, and we can go on and see that V1 is equal to 1 over U1, and so then what do we get? We get that V1 U2 is equal to Q. This is the same gluing that we had. Okay, which tells us that U2 is equal to QU1, which is Q squared U0. Okay, and we could continue this, and we'd end up finding that Uj was just some multiple Q to the J U0. These things have a name. They're called dilatations, I think. And so they're kind of these weird gluings of these copies here. Okay, so we have these infinite number of coordinates here. So this is really a scheme. Okay, using this formula, you can also see that 1 over Vj is going to be, well, this is going to be Q to the J 1 over V0, which tells us the next equation, which is that Q to the minus J V0 is equal to Vj. Okay, so we have this other expression for the infinite parameters here. Okay, and so this is kind of interesting that we have these kind of relations here. So I guess on the generic fiber, all these Q's are invertible. So note that on the generic fiber, we only need the coordinate U0. So we can actually just use U0 as kind of this canonical coordinate, and then note that when we specialize, you kind of have to be tricky about which coordinates you're using to look at what's going to be happening on the special fiber here. Okay. So that's what I wanted to say. Let me give you kind of okay. So this is kind of the basic version of this. There's another version. Let me say that there's kind of, like I said, that to actually talk about the theta function, we need to go to some cover, and so there's y double dot, there's y, and then there's x down here. So the stable model of our elliptic curve. Okay. And then here, what's going to happen is, okay, so we have our guy here, and so then we have, so I'm just going to draw the special fiber here. This goes down here. Okay, and then we have all these kind of marked points here, and corresponding to the point 1. And then this guy is going to be pretty much the same, except for we're going to get 2 copies of the marked points. So this is going to be degree 2. I'll say a little bit more about how this is constructed, but I guess this is all we need to know about this for now. So here, again, like I said, the coordinates here will be, so let's say this is the 0th coordinate. So we had U0. Then, oh, the coordinate here I'll just write as u0 dot dot. Okay, and and then this will be u0 or dot u minus 1 dot dot if this is u minus 1, etc., so on and so forth. And on each of these pieces, this is just the squaring map here. So that's just saying that uj dot dot squared is just uj. Okay, and so this is the relation between these two things, these coordinates here. And so this is a map of formal schemes. Again, this map here, this is a quotient map. This makes sense. There's a discrete action. So you can actually take this quotient in the category of formal schemes. All right, and we have these guys. And now, unlike before, we need to talk about, like before, we need to talk about what's happening here. So it turns out that at these intersections, these nodes, that we're going to have let's say uj plus 1, so we had, let me just write down this equation, then I'll do it up there. So uj plus 1 vj, this was equal to q, okay? And then when you specialize, this becomes 0, which is why you see that. But here, up here, we're going to have a square root. So uj plus 1 dot dot vj dot dot. So this is q to the 1/2. Okay, so we're actually going to build a lot more of these. There's going to be, this is kind of the babyest thing that you can do. Yeah, and this is kind of like the unwinding before that we saw of the circle in the Bogomolov-Zhang proofs. It's kind of similar. But the analogies with the Bogomolov-Zhang proof are a little different than just that, you know. Okay. All right, so we have what these things are, and now I want to go back to this infinite product formula and kind of show you what we can do with these things. So we had this theta dot dot u dot dot. Okay, so this is minus c over u, and then we had the product for j bigger than or equal to 0 of 1 minus q to the n u dot dot squared. So this is actually u0. Product j greater than or equal to 1 of 1 minus q to the j, so this is a j. Q to the j, oh dang it, well, q to the j, oh dang it, q to the j over u dot dot 0 squared. Okay, so that doesn't make sense. This is q to the j u dot dot 0 squared. Okay, so like we said before, with our relations, we have that q to the n u dot dot 0 squared. So this is really, well, we can bring it inside. And this is u dot dot j n, or sorry, u dot dot n squared. Oh man. U dot dot n squared. Okay, so because this is u to the u dot dot to the n. Okay, so that's cool. Also, we should notice that that q to the n over u0 dot dot. So this is equal to 1 over q to the minus j u dot dot 0 squared. This is 1 over, then we just bring it inside, j over 2 squared. So this is 1 over u to the minus j dot dot is equal to v dot dot to the minus j, like so. Okay. Great. Squareds everywhere. Okay. Okay, so now, using this, we see that this product becomes this over u0 dot dot times the product j bigger than or equal to 0 of 1 minus squared j, and we have this product for j bigger than or equal to 1 of 1 minus v minus j dot dot squared. Okay, so we have this kind of this formula that we have now in terms of all the different coordinates. Okay, and this is interesting because it does verify for us that so again, like I said, it's consistent with this thing that I was saying that that here we're going to have the specialization here of these torsion points. They're going to go here, and so now now we're going to have actually two of them once we do the dot dot version, and you can see this exactly from here. From this formula. So on the jth component, it kind of is going what's happening with the torsion point q to the 0. Okay? And on q to the 0, you're really going to look at plus and minus 1 as those 2 points there. And you can see that the 0 locus of u dot dot, so the zeros, okay, so these are exactly the sum for j and z q to the j squared over 2. So kind of the closures of these things. Okay, and so when we view these as log, so we'll kind of view these things as formal schemes with log structures. These are exactly the cusps. So these are what are called the cusps. Okay? All right, and okay, so we have our integral power series. Okay, we have our power series thing here. We looked at the zeros. Now I want to talk about the poles of this theta function. Okay, this is going to be important because in our reconstruction of theta, we're going to do this. We're going to do a lot of reconstruction, and we want to use. Well, we're kind of going to be using interpolation and using the fact that rigid analytic functions are really determined up to a multiple just by where their zeros are, and if you know their multiplicities. Okay, so what are these, the poles? So this is the next question that's on our list. Okay, so we had that kind of a baby version of the functional equation. So we had this expression that said that u0 to the so where's my functional equation? Okay, well, we had this thing, q to the 1/2 was equal to -1 over q to the 1/2 u dot dot 0 squared theta dot dot u0 dot dot. Okay, and there's kind of a more general version of this, if I can find it. So the more general version is when you have higher powers of q. So let me see if I can write this down. So it's u. So what do we have? Q to the a over 2. Okay, so this is equal to -1 to the a, q to the a squared over 2, so this is in the denominator now, u dot dot to the -2a, and theta dot dot like this. Okay, so this is kind of the more general version of the functional equation, which you get by repeating this thing a couple times. Okay, that's great. Well, okay, so this is good, and so now what I want to do is I kind of want to look at so I want to look at what happens to So to look at the poles, I want to look at what happens at the component labeled A. Okay, so let's bring this to the other side. Okay, and we see that this thing. So I'm solving for this. So this is equal to theta, and then we have q to the a over 2. Then we have -1 to the a. Then we have q to the a squared over 2 u0 dot dot minus 2. So if we're going to sign here, this is a plus. Okay, and this becomes, now we're going to apply our formula. This is u of a dot dot, -1 to the a. Then we have q to the a squared over 2. And now we have u a dot dot over q to the a over 2 to the 2a, like so. And this is now nice. This becomes this. Just write down the same thing. Okay, now this becomes q to the a squared over 2 minus, or q to the negative. Now we have a squared u dot dot a of 2. Okay, 2a there. Okay, and now this becomes, so now we have this big fat q to the a squared over 2. Bam! Okay, that took me forever to figure out. Okay, this thing here, so now we have this u dot dot to the a to the 2a. And if you want to look, if you want to see what I'm doing, look at proposition 1.4 of Etale Theta. Okay, so this is the expression for this, and now you can see this is a series. This is just this crazy series that we had, and it was actually integral, in positive integral. But it's you can see that at mod q it's going to vanish now. You can see from this formula that mod q it's going to vanish. And that you see that the vanishing on the component y of a is going to be a squared over 2. So let me just say that again. So the so minus. Okay, yeah, minus, because we want this to be a pole, because we're computing poles, remember? Okay, I do. Barely. Okay, so and now this shows us that the poles here, so this thing is this certain divisor, okay, and the divisor is, so it's divisor of this. So this is minus a squared over 2 times the order of vanishing of q times the 8th component here. So this is for a in the integers. Okay, so what we've done is we've kind of have, so okay, so what's the point? Is that we have our dude, right? Okay, we have y, okay, and this is the generic fiber, or K, I don't know, K, rigid fiber, whatever. Then we have the special fiber, and then we have all these dudes here, okay? So this Gaussian-like divisor, okay, is just this vertical piece here. So the poles of theta are kind of this vertical thing, and then so these are the poles. Okay, and then they're Gaussian-like with Gaussian distribution. Okay, and then the zeros of this dude, so the zeros correspond to the various cusps. Okay, so we're gonna have these dudes here, these kind of horizontal. Okay, so again, the zeros, so these are just kind of the cusps, and they're uniform. All right, so that's what we get for these guys. So that's so nice. Okay. All right, so that's all I wanted to say about this. This is the basic part. So what we're going to do next is we're going to try and is kind of reconstruct the theta function geometrically and give it a more geometric interpretation. The next step after that is to anabelionize that whole procedure. The next step after that is to shove it up a Frobenioid, right? To do this construction inside the monoids of a Frobenioid. And then after that, we play with it, this construction inside the Hodge theta. We kind of, well, we're going to, yeah, so I guess at this point I'd be saying really vague things, but I need to define a Hodge theta in order for some of these things to make sense. Thanks for watching. Bye.